Our second version of the fundamental theorem of calculus is this. If you have a function, f of x, that's continuous from a to b, and you can guess or you know an antiderivative of little f, then the definite integral of little f from a to b is just capital F of b minus capital F of a. So this is a great shortcut for evaluating definite integrals because a lot of the time we can guess an antiderivative for little f. This expression right here, this capital F, but evaluated at two places and subtracted, this shows up often enough that it's really nice to have some notation to abbreviate this so that we don't have to write out, right? Usually what we'll have is a formula for capital F, and we don't want to write out that formula twice if we don't have to. And so here's the notation that people usually use. To abbreviate at capital F, but with both bounds plugged in and subtracted, we'll write just a vertical bar next to capital F with the bounds in it, next to the vertical bar like this. Notice that the order that you put the bounds in is important because the top bound is first and the bottom bound is second, right? So order matters here. So with that in mind, let's use this second version of the fundamental theorem of calculus in some examples. So let's calculate the integral from -1 to 1 of 1 minus x squared. Right, so in the past, we would have had to do some big long calculation involving the limit of a Riemann sum, but now we know all we have to do is guess an antiderivative, make sure that it's a correct antiderivative, and then plug in the bounds. So first, let's guess an antiderivative. So an antiderivative for 1 is just x. An antiderivative for x squared is something like x cubed. But that's not right, because if you differentiate x cubed, this 3 would come down because of the power rule. So we need a 1/3 here, waiting to cancel it. So as soon as you write down an antiderivative, check that it's right just by differentiating. So derivative of x is 1 minus, and then derivative of 1/3 x cubed. The 3 comes down, cancels the third. You get x squared. Yes. So this antiderivative is correct. Remember, we still need to evaluate this from -1 to 1. And now we can plug in our bounds and see what we get. So when we plug in the first bound, we get 1 minus 1/3 times 1 cubed. And now we have to subtract and then plug in the bottom bound. So -1 minus, oh, I wrote half here instead of cubed, or 1/3, 1/3 -1 cubed. And now the calculus is done, we just need to do some arithmetic. So let's see, 1 minus 1/3 minus -1 plus 1/3, I guess. So this part is 2/3, this part is minus -2/3. Oh, and so we get 4/3 altogether. All right, you can see that all of the calculus happened right here. Right? Everything after that is just arithmetic. So all of our calculus took like 2 lines. That is way, way better than having to grind through a giant calculation involving a limit of a Riemann sum. Let's look at a couple more examples. So here's an example where we actually gave up on finding the value of this exactly because we decided it was too hard using the limit of a Riemann sum. But we don't have to use the limit of a Riemann sum anymore. We can use the fundamental theorem of calculus. So the fundamental theorem of calculus says, guess an antiderivative for your integrand function. And the antiderivative of sine of x is minus cosine of x. Don't forget that minus sign, right? Double check that this antiderivative is correct. The derivative of minus cosine, let's see, taking the derivative of cosine is minus sine, which cancels that minus, so this is right. And then evaluate at 0 and pi. All right, so minus. One nice trick involving this bar notation is constant multiples you can actually leave outside of the bar if you want. It's the same either way, but it's just less writing to leave it on the outside. Okay, so negative cosine of pi minus, and then plug in the bottom bound, cosine of 0. So negative cosine of pi, that's -1, minus cosine of 0 is 1. So this whole thing comes out to be 2. So right, the graph of sine from 0 to pi, like this, the area under here is exactly 2 units of area. It's a bit of a surprise that it comes out to be such a nice number. All right, one final example is calculating this definite integral from a to b of x squared dx. This is, we had a formula for this integral that involved a big long calculation, but with the fundamental theorem of calculus, we can come up with a formula for this integral in just a couple lines. So an antiderivative for x squared is 1/3 x cubed, and then we need to plug in our bounds, a and b. And again, you can either parenthesize it like this or like this. Right? This 1/3 is a constant multiple, so you can move it outside of the bar if you want. So 1/3, and then we'll plug in our bounds. So first plug in b, so b cubed, minus, and then plug in a cubed. And that is the formula that we got in a previous video, but it's much, much easier. It took 2 lines instead of like pages and pages. So you can see that the fundamental theorem of calculus, the second version of it, is an incredibly powerful tool for calculating definite integrals.